This is lab 6, controlling servo motors. So in this exercise 1, I have made the circuit here with the potentiometer there and my servo motor here, and it's all wired up. Then this is my Arduino code. So you can see right now it's at the 0 spot. So if I turn up the potentiometer, you can see it's moving. So for question 4, after many trials of changing my sketch and defining the pulse rate, no matter what I do, it can reach close to the 180 degrees, but it doesn't reach the full 180. And another problem is that that cracking sound does not leave. Like, no matter what I change the pulse rate to, it's always there. This is the best I've had with the least cracking and the most rotation with these pulse rates, which I already showed you in the code. So right now you can see it's at 0, and if you go to a servo monitor, you can see that pulse is at 550 and the angle is showing 0. And if I increase it, you can see the angle is increasing. And it goes to 180, and on here, it's 180. Moving on to exercise 2, question 1. The theory that we learned in class was this equation for V out and this equation for VLSB. So in our case, we have M equals 3 bits, or 3, and then we have VFSR is equal to 5 volts. And for the VLSB, you get 0.625 volts. And for the 8 different bit options, these are the V outs that you get in volts. So this is question 2 for the RTOR deck, and you can see that this is a 3-bit because it has 1, 2, and 3. I'm going to show you guys 2 cases. So in the first case, I'm going to represent the case where it's 0, 0, 0. So all these switches are off. And then when I run simulate, run DC solver, you can see it ran and you get 0 volts. This is the second case where the binary code is 0, 0, 1. So the least significant bit is on and the other 2 are off. And if I simulate it, you get 625 millivolts, which is equal to 0.625 volts. I followed that procedure for the rest of the binary codes. I showed you the first two, 0, 0 and 0, 0, 1. And for the rest of them, I followed it. I got the same thing as the theory, so the theory matches with the circuit lab. Okay, this is question 3, and this is my R2R DAC. And so I have 20k ohm resistors here, these big ones, and the small ones are 10k ohm resistors. And then I'm reading V out this blue wire into analog pin 1. This is my code for that. So this is the first example, and the code here is 101. So you can see this one is 1, power on, off, then this one's 1. Then you can see the voltage you get here is 3.125 volts. This is the second example, and you can see that all of the 3 are on, so the code is 111. And then when you come over here to the servo monitor, you can see that's 4.375 volts. So I repeated that for the rest of the binary codes, and then I have them right here, and you can see that they match the theory and simulation that we did before. So for this last question, if we needed smaller step sizes, what I would do is I would increase the number of bits. So basically in my physical circuit, you see how there's 1, 2, and 3 bits. I would add another rows here. That would make the VLSB smaller and thus increasing step size. Moving on to exercise 2, this is my code. So I define all the values at first, and this is my void setup, then void loop. And this is my circuit. I control it using these 3, D0, 1, and 2. So I'm going to show you a few examples. So this first example is when all the switches are on, so you can see they're on power, so 1, 1, 1, 1. If I go to my Arduino, you can see that it prints out 7 because that's the decimal code of 111. Prints out the V out, 4.375. It prints out the pulse rate, 2450, and that maps to the angle of 180. And that's what it looks like on the potentiometer. Next example I'm going to show you is 110. So if I move this from power to ground, you can see that this moved. So here, I'll show you again. So this is 111, and if I move to 110, you can see it moves. And now on our screen, you can see that the decimal code is 6 instead of 7, and the V out is 3.750. Then that reduces the pulse rate to 2178, and then we get an angle of 154. Lastly, so you see right now it's at 110, but if I make it all 0, 0, 0, so I move all these to ground, you can see the potentiometer moved to 0 degrees from 180. Now if you go to our screen here, you can see that the code is 0, the V out is 0, then our pulse rate is 550, the lowest it can be, and then we get an angle of 0 degrees. It accurately represents this table right here that we did in the simulation before. So I showed you these 2 examples and that example, and these ones work fine too. So it can be seen by if you change these 3 inputs that the amount of position you can change the servo to is only 6. Based on this table, you can only do 6. If you needed a smaller step size in the angular position, what you would do is add more of these rows of bits, so you have more inputs, and that will decrease the V LSB. By increasing the bits, we'll get more range in our codes, and that'll increase the V out, so then we can have different positions in our servo. So lastly, for the question, how does this compare to using the potentiometer exercise 1? Well, with the R2R DAC, you can't do more than 6 with the 3-bit DAC. And then the servo can only be in 6 spots, but with the potentiometer, you can vary the angle of the servo between the 0 and 180 degrees, so it can be between 0 and 5 volts. And in the DAC, we only have a certain range of voltages that we can work with. So basically, using the potentiometer is way more useful than using this R2R DAC for turning the servo motor.